Good day, students. In this clip, we're going to be going over the art of finding the definite integral. We're going to be reviewing most of the concepts we covered in chapter 5. So let's get started by taking a look at number 1. We're to use the given velocity time chart to estimate the distance covered by a traveling object in the first 24 seconds using left endpoint rectangular approximation. All right, so what we're looking for here is the distance covered in the first 5 seconds. So that distance is going to basically be given by the definite integral expression, the integral from 0 to 24, actually the first 24 seconds, of the velocity function dt. Okay, this expression gives you the exact distance covered from in the first 24 seconds. But we don't have a function here, so and we just have a chart. So the best we can do is approximate what the total distance covered is. So to calculate that, we're going to be finding an approximate value using the left-hand rectangular approximation. Okay. All right. So if you notice here, it looks like our intervals are not equal, so we cannot use the other formula for equal subintervals. Let me show you what that formula is. If you have equal subintervals, you can use the formula LRAM is basically W times f of x1 plus f of x2 plus the pattern goes on, f of xn minus 1. Okay, so this is when you have equal subintervals. In this case, our width or subintervals are not equal, so we cannot use this formula here. All right, so in order to determine what our various widths are, we're going to actually have to sketch the interval and compute what the width is. In this formula with equal subintervals, you can simply compute W by finding the length of the interval divided by the number of equal subintervals that you're going to use. Okay? Now let's draw a number line illustrating the range of our time interval. We're going from 0 all the way to 0 to 24. All right, so let's mark our calibrations. We're starting from 0, so this is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, we can see that our intervals are varying from 5 to 4 to 3, like that. They're not even. Okay, so let's enumerate our calibrations here. So we're going to have, this is x1, x2, x3, x4, x5, x6, and x7. Okay, so for your left rectangular approximation, you're going to pick all the points to the left of the right endpoint. So we're going to neglect x7 here. All right, so let's go ahead and find out what our widths are. So for W1, this right here is W1. W1 is equal to 5. You can close this 5. W2 is equal to 4. W3 is 4. W4 is 5. See how the subintervals are irregular. W5 is 3, and then the last with W6 is 3 also. Okay? Alright, so let me write down the formula that we're going to be using here. LRAM using 6 of intervals is going to be, let's see, W1 times f of x1 plus W2 times f of x2 plus W3 times f of x3 plus W4 times f of x4 plus W5 times f of x5 plus W6 times f of x6. Okay, so this is how it looks with the left-hand rectangular approximation. If we're doing right-hand rectangular approximation, we just start with x2, 3, 4, 5, 6, 7. Okay, so that's the difference. Now let's plug in our values in here and compute the approximate distance covered. All right, so W1 is 5 times f of 0 plus W2 is 4 times f of 5 plus W3 4 times f of 9 plus W4 5 times f of x4, which is 13, plus W5, which is 3 times f of 18, plus W6, which is 3 times f of 21. All right, so to find these output values, what we just simply do is make use of this chart right here to find out f0, 5, 9, 13. You all know that. Anyway, so let's go ahead and do that. We're going to have 5 times 0 plus 4 times 30 plus 4 times 50 plus 5 times 68 plus 3 times 82 plus the last one 3 times f of 21, which is 90. Alright, if you put all this together and calculate it, you're going to come out with 1176. What's the unit of our distance here? Meters. Okay, so this is the total distance the particle covered. Alright, let's take a look at question number 2. So for number 2, we're going to evaluate the definite integral. Evaluate the definite integral from -5 to 5 of the function 6 minus the square root of 25 minus x squared dx. Okay? Now this is a situation where we can make use of the geometry of the appearance of this function on this interval to compute what the area is. Okay, because we know the definite integral is basically the area between the curve and the x-axis. So what kind of function is this? What does it look like, the graph of this function? So you notice you have r squared minus x squared. This is automatically a semicircle with radius 5, but we have some translations and reflections happening here. So this minus means it's going to be looking at the bottom hemisphere, the bottom semicircle, sorry, and then 6 units involves a shift. Okay. All right. So before I graph it, let me write it in word form. So this portion right here, the integrand is a bottom semicircle shifted 6 units up. Okay, so that's basically the situation we're dealing with here. All right, let me give you a sketch of the situation, and then we can use that appearance to determine the area. All right, so there goes our coordinate system. Like that. All right, so there you have the semicircle, and it goes from -5 all the way to 5. It's centered at the origin, but we're to shift it 6 units up. Okay, so it's going to go 1, 2, 3, 4, 5, 6. We're going to shift this entire semicircle 6 units up. So let's go ahead and do that. Shift it up like this. Okay, so what we're looking for now, this is the resulting function, is the area underneath this curve. So between this function right here and the x-axis, that's the area that we're looking for. That is the value of this definite integral. All right? Okay, so you can clearly see that this is an easy geometry problem. We can visualize this as the difference between the area of a rectangle and the area of a semicircle. Right? So this is what we're looking for here, this area down here. So simply the entire thing is a rectangle, and then you subtract the semicircle from there. Okay, so let's go ahead and do that. So let's write it in word form. Area equals area of rectangle minus area of semicircle. Okay, so what is the area of the rectangle here? The entire length is 10 units, and it's 10 units wide, and you go up, and the length is 6 units. 1, 2, 3, 4, 5, 6. So the area of the rectangle is 6 times 10. Minus the area of the semicircle, the radius is clearly 5, so pi r squared divided by 2, so 1/2 pi r squared, 5 squared. Okay, do the calculations, you end up with 60 minus 25 pi over 2. All right, so this is the expression of the definite integral. Okay, so this is equal to, let's write on the left side of the expression what we're asked to find, the definite integral from -5 to 5 of 6 minus the square root of 25 minus x squared. Okay? Alright, so that's that. Alright, let's take a look at question number 3. This is another definite integral problem, so we have to evaluate the definite integral from pi over 3 to 5 pi over 6 of cosecant x cotangent x dx. Okay, so this is a problem where we can use the derivative, the antiderivative to find the integral here. Okay, so if you think about the antiderivative, what do you differentiate to get cosecant x cotangent x? Remember from your differentiation rules that the derivative d dx of cosecant x is equal to cosecant x cotangent x, negative cosecant x cotangent x, right? So this is a derivative. In order to compensate for this negativity, we know that the derivative d dx of negative cosecant x is simply going to be the opposite of that, which is cosecant x cotangent x. Okay, so using the derivative, here we can determine what the antiderivative is here. So if we evaluate the antiderivative of cosecant x cotangent x, that's going to become negative cosecant x, right, evaluated from pi over 3 all the way to 5 pi over 6. Alright, so what we're using now is FTC part 2. Basically, you find the antiderivative and you evaluate it at the upper limit minus the antiderivative at the lower limit. So this is going to become, and another thing we can do is factor out this minus so we don't keep using it over and over again. Let's put the minus on the outside. So negative um, parenthesis cosecant 5 pi over 6 minus cosecant pi over 3. All right, now so I'm going to evaluate these two. Cosecant 5 pi over 3 is 2 minus cosecant pi over 3 is 2 root 3 over 3. If you distribute the 2, I'm sorry, the negative to both quantities, you're going to have 2 root 3 over 3 minus 2. You can find the LCD, put this over 1, and then multiply this by 3 top and bottom. By 3, and then your final answer is going to be 2 root 3 minus 6 divided by 3. All right, so that's that. All right, let's shift our attention to question number 4. Question 4, we're to find dy dx. If y is equal to the integral from 4x squared to 5 of the square root of 1 plus 5 sine square t dt. Okay, so this is a FTC part 1 that we're going to be using here. In this case, you notice that we have a constant limit as the upper limit of integration, and we have a variable limit as a lower limit of integration. Okay, so remember the procedure for this. So y prime or dy dx is going to be, we're going to use a shortcut here. You're going to, we're going to substitute the upper limit into this function, which will be the square root of 1 plus 5 sine square 5. But when you multiply it by the derivative of this using the chain rule, you end up with 0. Okay? So evaluating the antiderivative of this, the derivative of the antiderivative of this function at 5, you get 0. Minus, if you evaluate this, the derivative of the antiderivative of this at 4x squared, all you have to do is simply plug in 4x squared into this function, which would be the square root of 1 plus 5 sine square. Instead of t, you're going to put in the 4x squared right there, and then multiply this by the derivative of 4x squared. So the derivative of 4x squared is 8x. Okay, so if you simplify this a little bit more, your final answer will be negative 8x times the square root of 1 plus 5 sine square 4x squared. This is an application of FTC part 1. All right, let's take a look at question number 5. So for question 5, we have to find the average value of a function. So find the average value of f of x equals negative 4 over 1 plus x squared on the interval negative root 3 all the way to 1. Okay, now the formula for an average value of f on an interval AB is given by the reciprocal of the length of the interval b minus a times the definite integral of the function from a to b, like that. Okay, all right, we can see in this problem that our a is the lower boundary of our interval, negative root 3, and b is the upper boundary of our interval, which is positive 1. Alright, so let's plug in a, b, and the function into our formula here. So the average value of our function is going to be 1 over b, 1 minus a, which is negative root 3, okay, times the definite integral from negative root 3 to 1 of the function negative 4 over 1 plus x squared dx. Okay? Alright, now thinking back to your differentiation rules, does this look familiar to you? To help juggle your memory, I'm going to factor out this negative 4 here from the integrand, so it becomes negative 4 over 1 plus root 3 times the definite integral from negative root 3 to 1 of 1 over 1 plus x squared dx. Do you remember the function that results in this function upon differentiation? Do you remember the derivative of your tan function? What's d dx of tan? Inverse tan, sorry. The derivative of inverse tan is 1 over 1 plus x squared, right? Alright, so we're going to apply that here. So this is going to become, let's change our color. This is going to become negative 4 over 1 plus root 3 times the inverse tan of x evaluated from negative root 3 all the way to 1. Okay, we're using FTC part 2 here. Evaluate the antiderivative of this function at this limits, the difference of those limits. So you're going to have negative 4 over 1 plus root 3 equals, times the inverse tan of the upper limit first minus the inverse tan of the lower limit. Okay, so that's what you're going to compute. Okay, so using your knowledge of trig, we can figure that this is negative 4 over 1 plus root 3 times inverse tan of 1 is pi over 4, and inverse tan of negative root 3 is negative pi over 3 there. And then we can find the LCD and simplify. Let's go ahead and do that real quick. So we have negative 4 over 1 plus root 3 times pi over 4 plus pi over 3. Okay, so if you find the LCD, you times this by 3 top and bottom. 3, and you times this by 4 top and bottom. And you combine it, you have negative 4 over 1 plus root 3 times 7 pi over 12. Okay? So let's simplify this a little bit further. 4 goes here 1, 4 goes here 3 times, and you're going to have negative 7 pi divided by 1 plus root 3. So let's simplify the denominator here, since we can have a radical in the denominator. So we're going to multiply by the conjugate of this radical right here. So 1 minus root 3 top and bottom. In the numerator, we'll simply have negative 7 pi times 1 minus root 3. And then in the denominator, this is a difference of squares in factored form. So if we multiply together, we just have 1 square minus root 3 square. there. So that's going to yield, oh yeah, we had a 3. Let's not forget that. There's a 3 down here. So I have a 3. And then we still have to retain that 3. Okay, so let's see. In the numerator, I have negative 7 pi times 1 minus root 3. And then in the denominator, we'll simplify it. Let's see what we get. We'll have 1 minus root 3 squared is just 3, right? So 1 minus 3 is going to give us positive 2. Negative 2 times 6 is going to give us, negative 2 times 3 is going to give us negative 6. Alright? So our final answer is simply going to be 7 pi times 1 minus root 3 over 6. Okay, because this minus is basically divide out, alright? So that's that. So thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel for other cool calculus clips such as this. And please post a comment to let me know what you think about this presentation. More clips can be found on math.serve.com/calculus. Thanks again for watching and have a wonderful day.